One of the most common questions in electronics thermal analysis is how to model heat generating components. Datasheets give some insight on performance, but often a lot of assumptions need to be made, and as the junction temperature is the most critical value for electronics analysis, it's crucial to get component modeling right. This is where IC thermal model calibration comes in. Let's focus on this Ethernet controller in the top left. It's currently modeled as a simple block with a volume heat source. Let's go through the process of creating a calibrated, detailed thermal model. FlowEFD includes the package creator for this very purpose. The Ethernet controller is a low-profile quad flat pack or LQFP. We give the package a name and select the size and number of leads, which we can get from the datasheet. If we don't know certain properties, we can accept the defaults. When the wizard is complete, we're in the package editor where we can make parametric changes. The package is displayed on screen and can be manipulated. We'll make the encapsulant transparent so we can see the internal details. We can see the die in red, the wire bonds, the lead frame and tie bar assembly along with all the materials. If we start by making some changes to dimensions, we can see the geometry update in real time. We're making the tie bar area larger as this dimension was physically measured. The lead offset is also adjusted to accommodate the larger tie bar area. The die source size is also reduced slightly. Once we're happy with the customizations, we can export the package in XT-XML format. Back over in FlowEFD, we can see where the import occurs with the XML import option. The geometry is automatically created and the FlowEFD project with all boundary conditions are present. When calibrating, it's crucial that the simulation matches the test setup as closely as possible. In this instance, there is a small thermal interface material under the component and it's mounted on a standard breakout board. The device was measured using the SimCenter Trista, which is a hardware test apparatus for characterizing semiconductor devices. Here we have the package structure function, which shows a graph of thermal capacitance versus thermal resistance. It gives insight into the various materials and contact resistances heat encounters as it leaves the package. One of the options available is to export a FlowTherm and FlowEFD calibration file. The steps of the calibration go like this. First, we identify the unknowns in the model. These are usually the material properties, i.e. the thermal conductivity and specific heat, the thermal contact resistances between parts, and some geometric unknowns such as the die source size. Second, we apply these parameters as input variables into a parametric design of experiments table. We can then give a min-max range for all the inputs to create a design space. The output parameter is the junction temperature goal. On the Calibration tab, we can see the measured response from the Trista, which we've imported. We don't need to calibrate the entire structure, only to the package case, which is approximately 9 degrees C per watt. This is the calibration extent. We can plot both the experimental and simulated structure functions on the screen and check the difference, which is quite large in this instance. Our goal is to adjust the input parameters to get the simulated structure function to match the experimental structure function. Let's skip over to a pre-calibrated project. Looking at the scenario table, we can see a series of simulations with varying input parameters to try and zero in on the experimental curve. This manual calibration took 16 simulations to get to the final result. We can now see that the structure functions overlap nicely, so we can assume this model is calibrated. What we've seen is the process of creating a package model and then calibrating its performance against physical test. This process gives accurate input data for both steady-state and transient simulations, which provides engineering confidence in the thermal results.